So, as we have seen that once you have set of features, so even in the neural network where you flatten your convolutional layer, the last layer, which is an image, and you flatten it. Your first row you write here, the second row you write here, the third row, and then it becomes a vector, a feature vector. And that you can pass it to any classifier if you're doing classification. Okay, so you pass it to, and so some of the supervised learning which can be used for classification as well as for regression is SVM. Okay, a support vector machine. So support vector machine is can be used for regression and classification. Just your objective changes. Once you are doing classification, so you have this data belongs to one class, this data belongs to another class, and you try to find the widest gap between the two classes, widest gap. So you try this margin to be maximum, okay, and you fit in, and these are called support vectors. This vector passing through these 2 points and the last point. So this is once you are doing classification. But if you are doing regression, then you try to make this thinnest and have maximum points get into this pipe. Okay, so though it's almost the same optimization problem, but you form it differently, and we will learn about what is slack. Okay, some of the points which are not coming in here, and sometimes there may be a point which is misclassified, and you still live with it. Okay, so we understand that for regression you try to fit in most of the points inside your plane, and for classification you try no point in the in this plane which you are fitting into between two support vectors. So this is something text that you can just read at yourself. So usually sometimes the data is not linear, like we saw in the linear regression case. So then there is a way that you try to put a separator. Okay, this is a separator which says yes, it is though it is not linear, so you cannot put a line, but there could be a separator which could just separate these two, and then it will just transform, and then transformed it into a way that where you could put a linear regression. So these are transformed. So your data, if it is linear, so you use this kernel, the polynomial kernel, radial basis function is something kernel of choice, and sigmoidal. So you can even deal with data which is not linear in SVM. So support vectors, it just says the same thing, that you have SVM, where first of all you find out is there that lie on the margins, are there like data points where you can put a separator to make them into two classes, and then try to have wider margin between the two categories. Okay, so I'll not get into the mathematics of this, but again the beauty of this is that you can convert it into a constraint optimization problem. A constraint, if you look here, this is the equation of a line which is in the center, and this is the equation of a line which is one support vector, which is weights into feature vector minus the bias is equal to -1. Weight into feature vector minus the bias is equal to 1. And the 0, and this would make this distance equal to 2 over the weights, the distance, the squares of the weights. And now if you want to maximize this, you got to minimize this. Okay, if the denominator is smaller, this whole thing will be bigger. So this maximization problem becomes a minimization problem mathematically. So that's how you basically, these are called support vectors, and this is how you mathematically write this problem, that you want to maximize this gap, and based on these two constraints, that this line should be greater than equal to 1 and this line should be less than equal to 1 for class 1 and class 2. And then you make this problem into a minimization problem, and putting yi, because once this is positive, yi is positive. Once it is negative, y is negative. So always it is greater than 1. So this is called a constraint optimization problem with an objective function and set of constraints. So this is called a constraint optimization problem, that for every xi you are going to write this constraint. So if you have 300 points, they are going to have 300 constraints. So if it is a positive point, so the weights once multiplied with the feature, with the bias, must be greater than or equal to 1, give you a positive value. If this is negative, then this must give you a negative, so that it becomes. So you write a constraint optimization problem putting all these constraints, and then there are ways to solve it. And once you solve it, you get a W, which are the weights, which basically plot this. So this is the SVM, and then there is sometimes. Once you are trying to fit in, this is a good example. Let me show you. Was this here? I think here. So this is an ideal support vector where all the points of one class is on one side and all the points of the other class are on the other side. But this is not really optimal. But if you make it a constraint optimization problem, like the one which I have shown you, guaranteed it will give you this solution, because you have asked it that know this point, because there is a constraint, otherwise it will violate the constraint. Know this point should be on this side and know this point should be on this side, because this is one of your constraints. So it will try to fit in, or otherwise it will come and say there is no solution exists. Okay. So, but if you give it a leverage that I don't mind even if this point is here, this point of this class is on this side, and there may be a point of this class which is on this side. You say, I would live with it, give me a wider margin. So my optimization is that give me this, and you put a penalty on this misclassification. There is a penalty. I don't want you to have many of these points on the other side, and you control the penalty. This is again called regularization, that you are controlling the penalty, but you are saying, I don't mind if this green point is on this side and this red point is in this within here, or it is even on the other side. Okay, you say I don't mind. Okay? So you reformulate the problem, and this reformulation is where you are saying I don't mind this. Okay, it's not greater than or equal to 1, but now you have it minus eta I. Okay, for every point you are giving it leverage to be on the other side as well. I don't mind, you may be on the other side. Okay, it's fine. But then you are saying, because a minimization problem, and if there is any point which is misclassified, I am paying a penalty. And with the C you control that, how much penalty, how much you allow this disobedience, so to say, to happen. But now it becomes a different optimization problem. Okay, so that's the beauty of the math, that, and especially the formulation of a constraint optimization problem. It's the beauty of constraint optimization problem, that you have now changed that to a very strict rule that this is not allowed, this is not allowed. Go find me a solution. And I say, okay, it is allowed, but there is a penalty. There is a penalty because an optimization problem, you are adding something. Okay, the more you put these, and with the C I control that how much should you be penalized. If you put a high value of C, it will make sure that very few points where it is really getting a lot of gain on this, it becomes a trade-off. You say, I am getting a lot of gain on this margin, so I can really increase the margin by only having 2 points which are misclassified. But then you're saying like 10 points are misclassified, but you are keeping C very small, 0.0 something, and you say even 10 points are fine, still I'm just trying. So with the C you control that how much this disobedience you are allowing in your support vector machine model, and same is the case if you are doing regression. regression, as I mentioned earlier. You want every point to be inside this pipe, or you say, I don't mind if some points are outside my pipe, I don't mind, but I'll put a penalty. Okay, and this penalty is, though I want everything to be within this margin, so this is a hard constraint. You put every point has to be inside this, and you increase the margin, and then you say, relax, no issue. Okay, if there are few points which may be outliers, so I would just deal with the outliers by having them to be just outside my. So this is the.
Sir, SVM is always performed on 2 features at a time.
No. You can have multiple features as well. For example, I'll just show you a code. जी बताएं. Yes.
सर ये जो आपने मार्जिन मैक्सिमाइजिंग दी मार्जिन की बात की, यदि वो ओवरफिटिंग और अंडरफिटिंग वाले कॉन्सेप्ट आते हैं.
नहीं. It's not really. जी हाँ. मैक्सिमाइज क्यों करना चाह रहे हैं? मैक्सिमाइज इसलिए करना चाह रहे हैं कि दिस इज ऑन द ट्रेनिंग डेटा. जैसे ही आप टेस्ट का डेटा लाओगे, देयर मे बी इंस्टेंसेस जो यहाँ इसके अंदर होंगे. ठीक है, अब ये बहुत ही नैरो मार्जिन है. ठीक है, बट बिकॉज दिस इज ओनली द ट्रेनिंग डेटा, यू डोंट नो कि जब टेस्ट डेटा आएगा तो उसमें क्या होगा. ये काइंड ऑफ ओवरफिटिंग की प्रॉब्लम है कि आपने इतना स्ट्रिक्ट कंस्ट्रेंट दे दिया है, कंस्ट्रेंट ऑप्टिमाइजेशन प्रॉब्लम को. सो इट इज अ मैथमेटिकल एक्सप्रेशन विच यू आर नॉट अलाउइंग एनी पॉइंट टू बी ऑन द अदर साइड. तो वो बहुत ही नैरो हो गया ट्रेनिंग में, और जैसे ही आपने टेस्ट किया आपने कहा ये तो इतने बुरे रिजल्ट आए मेरे. ठीक है, सो आई रियली डोंट लाइक, आई शुड हैव वाइडर. जी बिल्कुल, जितना आपने यू नो इट इज काइंड ऑफ लाइक अ डिजीज दैट यू आर ऑन द बॉर्डर लाइन, से यू आर ऑन अ बॉर्डर लाइन, बट if you have like away from the border line, you are happy that I'm quite away from the border line, so you are just this azan ho rahi hai. So now we understand that this is one where you have a constraint where every point has to kind of obey these constraints. So the solution would ensure that this constraint is met for, we say, all I. For every point has to be within this, okay? And there may be an outlier, let's say here, so it will increase because there is no way that it will allow this outlier to live outside this pipe. So if there is an outlier, it will be like this, and it'll just basically corrupt or your estimation. So not good. So this has zero tolerance for anything going outside this model, which obviously you don't like. You want here some points, you want to allow some points to be outside, and if you are allowing these outside, the same is the case with your model. Will have the provision with some. So this is where you are allowing this to be outside. You're allowing this to be outside, but you are saying, wow, there's going to be a penalty which you have to pay if something is outside. And so now you have this constraint relaxed. You have relaxed this constraint for every variable. So every data point xi, yi, it can be outside this epsilon, and this is how much it could be, but you pay a penalty here, this. And so because it's a constraint optimization problem, depending upon value of C, it by itself will do the best trade-off. Okay, the best trade-off, you don't have to worry about it. With the C, you are controlling that what do you want to value more. Okay, the C you are controlling what do you want to value more. But what if there is a non-linearity in the data? Then there are two things that you can do. First, you can play with the individual features, and you can just, like we saw, features, if you convert these features into polar coordinates. Okay, so all r and theta, so this is r and theta, all these smaller r with all values of theta, all these points will come on one side, all the other points which have larger value of the radius will be on the other side. Okay. So by transforming the features, nonlinear transformation of the features, you can still fit in a linear plane, or you use a kernel function to deal with the nonlinearity in your data. So these are some of the kernel function, RBF kernel and polynomial kernel. So you can see here, which is blue color, is the polynomial, and the RBF is shown with the green color. So here is the, on the iris data, you can see, as also it answers your questions, that now the iris data has 3 classes. So if you look at the decision boundaries, it will have something like this: 1, 2, and 3. Okay. So this is where you are using either you are transforming the features, or you are using a kernel. So I asked ChatGPT to generate Python code to implement sport vector machine classification on some benchmark data. Can we also plot the sport vectors? So I ask it. So as you can see, by default, sport vector machine uses RBF. Okay, so it's by default, and then it just do the training and then the classification, and then almost perfect classification it has done. As you can see, the confusion matrix, all zeros, 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 zeros. So all 10s are rightly classified, 9 and 11. So perfect classification. Everything is perfectly done through a sport vector machine with a kernel. So sport vector machine is a good kernel. So this also shows the sport vector, because nonlinear is just showing you all the points which are part of the sport vector, the boundaries. So